Finding relationships from data. Consider a situation of exponential growth. A scientist makes a prediction that the growth of a bacterial colony will follow the relationship P equals A multiplied by B to the power T. The following observations are made. Let's just assume this is possible. I'm guessing that there is no bacterial culture that will grow like this. And we're going to say P is the actual number of bacteria and T is the time in days. So 0 days, 5 days, 10, 15, 20, and these are the numbers of bacteria. Consider graphing P against T. So what we're going to do is plot these points. So we've got 0, 1200, 5 and 1320, 10, 1480, 15, 1640, and 20, 1750. Now I know the actual line I've used for this, and here is the actual line. And in real situations, the actual line will not exactly go through points. In fact, this is obviously a made-up example because real experiments often don't fit as close to the line as these points are. Now, the proposed model for this was that P was equal to A multiplied by B to the power T. Let's take logs of both sides. I'm going to go with natural logs. So I've got ln A multiplied by B to the power T. So ln P, using our log laws, ln A plus ln B to the power T. So ln P could be written as T ln B plus ln A. Note that's now of the form y equals mx plus c. It's a straight line. Not only that, but we can recognize that log b is the gradient and log a is the intercept. So that means plotting t against the natural log of p. So note that the y-axis has now become ln p. And we're going to plot these values against these values. So 7.09, 7.19, 7.30, 7.40, 7.47, and then we fit a line through those as best we can. Now we can work out the gradient. It's 15 across and 0.3 up. So ln A is 7.09. Remember, ln A, we said that was the intercept. And therefore, ln B is the gradient, which is 0.3 over 15 here. So that comes to 0.02. So A is going to be e to the power 7.09, just taking the exponential function of both sides, which puts that at approximately 1200. And then B would be e to the power of 0.02, which puts that approximately at 1.02. And actually, 1200 and 1.02 were the actual values that I used in order to produce the values in the table. Now remember, the equation was, or the proposed model was A multiplied by B to the power T, and therefore we now have P is equal to 1200 times 0.2 to the power T as our model for this bacterial growth.